Hi Astro Addicts, my name is Tim and welcome back to Astro Addict. And welcome back to explaining PixInsight part 4. In the last video we talked about the background modelization, getting rid of light pollution and gradients in your image. And now we pick up exactly where we left off. The image as you see right here and the sky survey image from the ESO observatory. And we will not need this anymore, so I will delete the icon for this one. And the next step is deconvolution. Now deconvolution is a process that I've seen someone else describe it as a process that you spend 3 hours on and then throw it away in rage and frustration. And my experiences are kind of the same. Let's begin. I will load my process icons, which I created for the deconvolution a few minutes ago. Here they are. And I created this little plot I will show you in just a few seconds. The tools we need for the deconvolution. This is just again, just for clarity, deconvolution. We generally need 4 tools for this one. We want to generate a point spread function. I will tell you what that is in just a second. We will have to create 2 masks. First a range mask, protecting the background of the image. And we will have to create a star mask, protecting the brightest stars in the image. And, as I said earlier, pure rage and despair, the deconvolution tool. Now you can find the deconvolution in the deconvolution option. There it is. And the convolution the directly opposite. It's nice to see what this does, and maybe it helps explain a little bit more what everything does. Let me show you. What is deconvolution? Right here we have the convolution tool, the opposite of this one. I will apply it to the image, and you see the image got blurred, like a Gaussian blur for example. I could also increase this, and amazing blur. So what is the deconvolution then? Deconvolution is a sharpening tool made to counteract the atmospheric seeing in your image. Most sharpening tools in most softwares are artificial. They try to create sharpness where none exists. But deconvolution is a process that looks at the stars in your image, tries to calculate how those should have been without atmospheric seeing, and calculates the optimal condition the image could have looked like if the atmosphere was not there. And therefore calculating these convoluted stars back to a non-convoluted state and applying this effect also to the nebula in our image. But let me explain it at this example. I created a plot of this image right here using the script render and 3D plot script. This is a plot of the Pac-Man nebula as you see right here. We can see a little bit of color change in the middle, but not very high data, let's say. And every spike you see here is a star. The X and Y axis are of course the image plane, and the brightness in the image is converted to the Z axis of this plot right here. Unfortunately I cannot turn this right now, so we're looking at this kinda from the side look, but I can't change the angle. I can only pan around in this image right here. Let's take a look at the stars. So, I really enjoy looking at this, it looks very cool. Alright, we have a noisy background. Everything looking green, maybe some orange in here, some color changes, but that doesn't really matter. We have very small stars, just tiny spikes out of the noise. We have normal size stars. So these stars reach from dark blue to turquoise, let's say, almost white. White would mean that the stars would have reached their maximum and are saturated. Generally you want to avoid saturated stars in your image. They lose color, they look blotchy and they're too big. And they can't be deconvoluted. Let's look at an example for this one. You see this very bright star right here. The top is flat, there is no data up here. Performing a deconvolution on this star would bring no benefit and it will only make things worse. On the other hand, performing the atmospheric correction on a very small star, let's look at this one here for example, the benefit would also be not very high and it would also deconvolute the noise in the background and make it even noisier. Very bad. For this deconvolution, the deconvolution is mainly used for the stars and the imaging data, not on the background and the noise. For this deconvolution, we can sample stars we choose. So in general, we want to choose stars that are not saturated and not close to being saturated. So this one here would already be too much. I guess a good star would be this one right here. It's bright enough, not very small, and it's not saturated and not on the edge of being saturated. And the basic premise behind the convolution is a point spread function. Let's look at this. If we think about stars, stars are gigantic blobs of helium, mainly. But they are so far away that each star in our image should be as big or even smaller than 1 pixel, because they are so tremendously far away from us. But the atmospheric seeing spreads this point out to, let's say, a Gaussian function, maybe, if you ever heard about that. So this point spread function is what we want to get from our stars. I can close the plot tool right now, and we create our own point spread function for our particular image on the left right here. The dynamic PSF tool is under Process, All Process, and it's a dynamic down here. I will activate it. There are lots of different values which we could use. The main things I use to get a good point spread function. I will disable automatic. The best point spread function for our stars is a Moffat star. It's different from the Gaussian function. The Gaussian value is described to convolute or blur everything, basically photography and imaging we have on Earth. But the Moffat function is made for astronomical conditions. I will check Moffat right here. I will maybe spread out this window a little bit more so we can see. And now we click on the stars in our image and take their functions into account. I've told you earlier that the stars on the edges here are not round, they are maybe ellipse shaped because of the edge distortion in my images. I still need to get the field flattener right, so choosing these stars would be very bad. Let's choose some stars in the center of the image. You can see right here this star is maybe way too much saturated. Let's click on this, and the information on all 3 color channels is shown here. The values I look out for are that we have Moffat functions and the amplitude of the star. Basically, the amplitude, how high the peak of this star is. I usually choose an amplitude between 0.2 and 0.8. Everything in between those values is fine. Everything below would be a too small star, deconvoluting the background too much. And everything above this value would not give us any benefit because the star would be only, but no extra information in the center of the star itself. So this is too much. 0.87, too much for my liking. Let's delete this one. And now we can pan around and choose stars we want. Let's pick this one. 0.04, way too little. Alright, let me delete this one. Let me take a look. This one right here, 0.26, that's okay. This one right here, 0.3. We want to choose maybe 30 to 40 stars to get a good average point spread function in our image. This one here, way too bright, 0.9. Let's delete this one. This one, 0.3, yes. Now, here we're getting too close to the edge of the screen. This one could be good. 0.84, too much. 2.4. Now on this one I maybe misclicked. Sometimes it happens that there's an error and the star is not recognized. Let's delete these values. This one could be good, yes. This one is too small. Just look at the amplitude value again. We can also choose the stars close to the nebula. Let's go for this one. And I think it doesn't detect the star very good here because the values are not given. Sample this, 0.7, just on the edge of being too much saturated, but it's good. Everything below 0.8 is nice. This one is too small. This one is too big. And you may see this process is very time consuming, but I like to create the point spread function myself. Too bright. You can see 27 stars right here. Maybe let's choose this one. Looks good. Too bright. Perfect. Too small. This one looks good. Nope, it's too bright. And I will just generate all these point spread functions here. Hang on. Alright, I think I've chosen enough stars. We have 40 stars, just sampled, right? Maybe close to the center of the screen, not in the edges. There are so many values here. I only look at the amplitude. The things you could look out for are the sharpness of the stars, the full width half maximum, and the eccentricity, I think it's called, the roundness, that they are round spheres and not ellipse shaped. But this looks good. Now we want to generate our point spread function for this image. The camera icon down here does exactly that. Now this, let me zoom in, is a synthetic point spread function for our average star. I can also stretch this one. And this is what we want to use in our deconvolution. I will close the dynamic tool, put this over here. And this template is now used to calculate how the image could have looked without atmospheric seeing. The next steps, as I said, we want to perform the deconvolution on the nebula data and on the stars. But not on the brightest stars, we want to choose the medium stars and not the background. Deconvoluting background where there is no data would only make it noisier. So let's use masks to protect the background at first. I have the range selection tool here. I will generate a real-time preview. Just in this case, so the preview of the entire image. This works pretty fast. And let me remind you, this image is still linear. So, like this. Generating a range selection from the linear image is kind of annoying because we have to work with very fine values. I will do a video about masking, I think, in the next part, because masking will be a very essential skill to have in PixInsight. I can't use this slider because it's just instantly gone. Maybe 3. How about 2.5? How about 1? Alright, here we have it. I think this mask protects most of the background and now has most of the nebula and the stars in it. This looks fine. And we have our mask. Close the range selection, minimize the point spread function. And as stated in the previous video, apply this mask to our image. White selects and dark protects. The background is protected now. Apply the mask to the image. We can now on the mask, the rendering mode maybe multiply. Nah. We can. The mask is still there, showing it. We look like this. The background is now protected. Now let's create a mask to protect the brightest stars, because deconvoluting them will only result in errors. The star mask tool, found in process all and on the right here, star mask. Again, I will do a video very soon on masking. I will just do a quick walkthrough on this one. I usually bump up the noise threshold. I want to include the big stars, not smooth them too much. And the midtones define how many stars it will take into account. I think a value of 3 or 0.3 will be good. Let's look at this. It will generate the mask. And again, if you want to try multiple values, you can use a preview, a small preview, and it will calculate it very fast. And you can take these settings on the big image if you're happy with it. I can hear the fans of my PC turning up because this takes a lot of calculating power. Our star mask has been created and I think it looks good. Most of the brightest stars are selected. But the problem is now, we can't apply two masks to one image. So how do we protect the stars now? Let's open the deconvolution tool. Pure H and its pair, deconvolution. We have the options to either use a parametric point spread function, a motion blur point spread function. No, we created our own, an external point spread function. Let's choose our PSF. And now let's walk through the settings you can do right here. The algorithm, the best algorithm is the, I will not try to pronounce this in English, this one right here. The iterations, usually the best value is between 80 and 100. I will use just 10 to maybe fine-tune these and then increase it to 100. The most important one is de-ringing because it counteracts the errors that this tool creates. And the wavelets, just a simple noise reduction. Leave it enabled, we don't need to change anything here. And the dynamic range. This image does not need any dynamic range, so let's not change any values. At first, we activate de-ringing. I will set all of this to 0. And now let's protect the bright stars. We have the option of local de-ringing. I will, as a local support image, it's called star mask. And now the brightest stars are protected and affected less by this deconvolution because they would only create errors because they are saturated. The local amount setting is fine usually. And now we could take our first step and apply this deconvolution. I will create a preview using over here. When creating a preview for deconvolution, you need to be careful because the size of the preview will affect the result of the deconvolution. So ideally, you want to choose the entire image as a preview, but this could take so much time to calculate each step. Let's choose a preview which has lots of stars, nebulosity, and is sufficiently big. I think this one will be good. This is our preview. I will make it bigger. This looks good. With 10 iterations, the target the luminance channel, not the RGB, always luminance, and the global dark and global bright, how much the dark and bright stars, how much the dark and bright areas will be affected by the error compensation. We have no compensation right now, let's apply. This could go quite fast. And it's done. Ugh, awful. Let's inspect the errors the tool made. On most of the stars we have, as you can see, the bright stars are protected and the background did not change. So our tools work. Maybe some things in the background, maybe we need to refine our masks. Alright, most of the stars have black rings around them. These are known as artifacts, maybe as raccoon eyes. And some stars have, in the other side, bright rings around them. So getting rid of the dark rings and the bright rings are the main steps of the de-ringing global dark and global bright. Usually these values are very small. I think the global bright of 0.001 will be sufficient. Let's apply this again and check if the bright rings have disappeared. And they did. Not as much as I like them. There are still some around here. Double this value. And check again. And that's why we want to create a preview, but a sufficiently big preview. I still see some around here. Again, let me remind you, 10 iterations right now. It will go through these steps 10 times. I still don't like it. 0.4. Usually the global bright is not that much affected by the iterations. I will leave this now as it is. And let's look at the nebula data. Let's look at this hydrogen pillar, for example. Redo. Some data has been altered there, but not that much, because the iterations are still very small. Now let's try to get rid of the dark rings around the stars by increasing the global dark. And this value is usually a tiny bit bigger than the global bright. Apply again. Now, if the opposite of dark rings happens, it means that your global dark is way too bright. This value is too big. Let's divide this by 2, apply again. And with 10 iterations and the correct global dark and bright, something like this could happen. Well, the stars are still... What should happen? The stars could be crunched up, made smaller, but the center should be brighter. This is what you want to look out for, and it does not happen right now. Let's look at some nebula data. Here's the pillar. Redo. Nothing changed. The error correction is pretty good right now. Let's increase this. I will. Usually what I do, I double these values and also double these. Let's apply again. Oh, let's apply again. 20 iterations, it will now take twice as long, and the local divergence, the warning, as you see here, is never a good sign at deconvolution. So maybe yes, awful. So these errors, you don't want to mess with any of these. To learn deconvolution, you play with the iterations and the global dark and global bright. If you manage to balance all of these, your image will look awesome. I will now go after my experience and stomach feel, let's say. Let's start with 80 iterations. Global dark of 2 here. And this is too bright still, I think. Let's try this one. 80 iterations, it will take a lot of time. And each iteration could take even longer if your image is large. Performing 100 iterations on my Hard Nebula image was awful. It took, I think, 2 hours each time, which is insane. And I couldn't use a very good preview because the stars in this mosaic have been very small. I think each time I will apply this now, I will skip through the calculation part and show you the result right away. Alright, so we can see we need more global dark and even more global bright. Undo and apply again. And as we see right here, I hate this. As we can see right here, I think our global darks and brights have been way too high. Let's try something like this and do it again. Creating a tutorial series like this is still very new to me, and maybe you could leave your opinion in the comments down below what you think of this, what you like and what you don't like about these series. And one thing I want to know is if you want maybe some very small background music to maybe make it a little bit more entertaining. But I will maybe start a small poll on YouTube on this one and ask some questions how I can improve this series right now. And I think this was quite good. This apply right here. Let's look at some stars. I will undo. As you can see, some of the smaller stars are now brighter. The stars that are protected by the mask did not change that much. Some detail is coming through right here. Some brighter edges, making more accutance, more synthetic resolution. The dark areas, let's check those. The small stars are brighter and smaller. As you can see in this one, for example, the center is getting a small spike in brightness. Let's zoom in as much as we can. Undo and redo. The noise in the background is not altered. Maybe some two thin stars are taken into account. 100 iterations, the stars are not shrinking that much, but they are pronounced well more. And working with these stars in star masking and shrinking in the end is way easier. And I think our detail in the nebula comes through a little bit better. I think I quite like this one here actually. Generally you want to use a global dark and bright exactly in the right spot when it's exactly enough to have your errors disappear. Using, like applying this right here, awful. You want to choose a global dark and bright, which is just enough to get rid of the errors, but not too much to have again created more errors. I hope you understood the basic premise of deconvolution. I will now try again and again and again. I will not show the final result because you need your experiences. Performing this tool on your images can be very different. It's the basic steps, and you can gather more experience by doing it on your own and not by somebody else showing it on an image that you don't have. You can't really learn from how to perform it exactly. So try this on your images, your nebulae, your star clusters, your galaxies. I will perform it right now and reach the value I like to be able to progress to the next step in the series. And I think right now the next step will be a little bit more explaining. First masking and then wavelet layers, because they will become very important very soon. Alright, that's it on deconvolution. If you have any questions, you can of course leave them in the comments down below. My name is Tim, I'm an astro addict. I wish you clear skies and may the night be with us.